Okay, one last lecture video for forces. Now that we have a pretty good understanding of forces and how to resolve them, we're going to talk about static equilibrium, free body diagrams, and how to draw them, and finish with static analysis. And that's the extent of it for the first year course. We'll leave the dynamic analysis fun for second year. So after the last lecture video, we should have a pretty good understanding of what an external force is, how to determine the external forces that are acting on an object, and how to determine that net or resultant force if all of the external forces that act on an object are known. And what we've learned so far will be useful in our analysis of an object at rest or moving with a constant velocity. In each of these cases, the external forces acting on the object are in equilibrium and they result in a net force of 0. If the net force wasn't 0, then the object would be accelerating as a result of these unequal forces. If the object is at rest, then the forces are in equilibrium and the object is described as being in a state of static equilibrium. So, static equilibrium is a state or a condition of an object that results when the object is at rest or is moving at a constant velocity. And the branch of mechanics dealing with the study of objects in static equilibrium is called statics. And I guess that makes a lot of sense. So in the first and second videos, we talked about Newton's second and third laws of motion. Now we're concerning ourselves with the first law of motion. So that law states that an object at rest will remain at rest and an object in motion will remain in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So basically, if there is no force, then there's no change in velocity. And in this case, no force means no net force. We know that force is equal to mass times acceleration, but if there's no acceleration because the object is at rest or it's moving at a constant velocity, then the sum of all the forces is also 0, right? So if A is 0, then F equals ma is equal to 0. It's important to note that this does not mean that there are no forces acting on the object or on the system. There can, and there usually are, still forces acting on the system. It just means that they're all equal and opposite, so they cancel each other out to have a net force of 0. Okay, so in static equilibrium, we know that the forces sum to 0, and we also know that the object continues in its state of rest or constant velocity unless it's acted upon. So at the instant where the picture was taken in each of these cases, you can assume that there is some sort of static equilibrium. So that is, all of the forces acting on the individuals cancel each other out and make it so that the person in each picture is not moving at that instant in time. So if we take the person pushing up against the wall, you can imagine that the force of the wall is equal and opposite the force that the person is pushing with. So that person is not moving. And you can justify the same sort of static equilibrium in each of these pictures. Statics enables us to analyze two types of situations. In the first situation, we may know that an object, such as a person, is not moving, but we may want to know what external forces are acting on the person. So for example, in gymnastics, a gymnast coach may want to know how strong a gymnast must be in order to hold a certain position, such as an iron cross in this picture here. So a static analysis of the position would give the coach this knowledge of the forces that the athlete would have to withstand in order to hold that position. And then the coach could test the athlete to determine if they were strong enough to react to those external forces, whose magnitudes were determined by your static analysis. Now, in the second situation, we may know what forces are acting on the athlete, but we want to know if these forces will result in static equilibrium. So if we take our gymnast again as an example, the coach may know how strong the gymnast is and thus how large the external forces are to which the gymnast can react. A static analysis of the position in question could then be done to determine whether or not the gymnast's strength is great enough to hold that position. Okay, let's focus on free body diagrams for a bit. So we talked about them very briefly in the last video, but we'll dive in a little bit deeper in this video here. So let's start with a simple situation to see if we remember free body diagrams from that last video. So a person in skates is just standing on the ice, just like in this picture here. And this person's mass is 70 kilograms. So in a free body diagram, we want to know what external forces are acting on the object, which in this case is this person here on skates. One force that we know acts on the person is the force of gravity, which is the same as the person's weight. And that always stems from the center of gravity. Okay, so the force of gravity would go on the diagram around here. And the force of gravity should point downwards from that center of gravity. And the center of gravity is the point at which the entire weight of the body may be assumed to be concentrated. So it's the point of balance of the body. Now, the force of gravity can't be the only force acting on the person. Otherwise, he would be accelerating downwards at 9.81 meters per second squared as a result of this force of gravity. Because this person is not accelerating downwards, then another force must be acting that cancels out the effect of the force of gravity. So the person's skates are touching the ice and exerting a force on the ice. The ice is thus exerting a force on the person as well, right? Action, reaction. That's Newton's third law. For every action, there's an equal and opposite reaction. So if we drew an arrow representing this force, it would be an upward arrow whose arrowhead is just contacting the skate. So that's the point of application of that reaction force from the ice. Now, I purposely picked this picture that is only the figure skater alone, isolated from the rest of the environment, because that's basically the essence of a free body diagram. Here, in a free body diagram, we only draw the object of interest, which in this case is the figure skater, and then any points where the skater touches something external, which would be where external forces may be acting. So just remember that in a free body diagram, only the object in question is drawn, along with all of the external forces that act on it. So just to recap, to draw a free body diagram of any situation, first, the system in question is isolated from its environment, and then the reaction forces are drawn as arrows at the points of contact of the system with the environment. The non-contact force of gravity is also drawn as an arrow acting downwards from the center of gravity of the system. So this is another example here. This is a picture, and if you were to draw a free body diagram, you would just take the person as your object of interest, and you would have the force of gravity acting downwards, and then you would have this ground reaction force from the Bosu ball pushing upwards on the person. So in the previous slides, we drew a free body diagram that shows all the external forces acting on the skater. And now we want to complete our static analysis. So if an object is not moving, it's in static equilibrium. And in static equilibrium, acceleration is 0, and the sum of all external forces acting on the object is 0. So mathematically, this can be described with an equation. The sum, this is the symbol here for the sum of the forces, is equal to 0. And this is the equation for static equilibrium. As simple as that. The term on the left represents the net external force, or the vector sum of all external forces. So if we get back to the analysis about the figure skater, The upward reaction force that the ice exerts on the skater has a positive sign because it's acting upwards, but we don't know how large that force is yet. The downward force of gravity that acts on the skater has a negative sign because it's downwards. And we said that the skater's mass was 70 kilograms. So first thing to figure out is, what is the skater's weight, or what is the force of gravity? And we know that F equals ma, so mass of 70 kilograms times acceleration due to gravity gives us a weight or a force of gravity of negative 687 newtons, or in other words, 687 newtons downwards on the skater. Now we can write the equilibrium equation for the skater. So the sum of the forces is equal to the force of gravity plus the force that the ice is exerting on the skater. So the reaction force from the ice is basically just rearranging the equation the opposite of the force of gravity, right? And that's what we get here when we plug everything into our equilibrium equation. So the force that the ice exerts on the skater is plus 687 newtons, or 687 newtons acting upwards. Now, this is true in all situations of static equilibrium where only two external forces act. So in this case, we had force of gravity and force from the ice. Those are our two external forces. The external forces need to be equal in size, but they act in opposite directions. So here's another example. We have an 80 kilogram weightlifter that lifted 100 kilograms over his head, and he's holding it still. He and the barbell are both in static equilibrium, and we're trying to find the reaction force from the floor that must act on the weightlifter's feet. So first, we need to draw the free body diagram, and we have three external forces that act on the weightlifter here. We have the reaction force from the floor acting upwards on the athlete's feet. That's the first one. Then we have the weight of the athlete acting downwards through the center of gravity. That's the second force. And then we also have the reaction force from the barbell that's acting downwards on the athlete's hand. So those are our three external forces in this case. And we still have one equilibrium equation, but we have two unknown forces. We have the reaction force from the ground, this one down here, and we have the reaction force from the barbell acting down on the athlete's hands. So that's too many unknowns for one equation. So we need a different equation to find one of these two unknown forces. To determine the reaction force from the barbell, we need to know the mass of the barbell so that we can calculate its weight, which is equivalent to the reaction force that's acting on the athlete. So let's say that the barbell has a mass of 100 kilograms. Then we can use our F equals ma equation and find that the force of the barbell is 981 newtons acting downwards on the athlete. We also know the mass of the athlete, which is 80 kilograms. So using that same equation, we find the force of gravity to be negative 785 newtons, right? It's in the same direction as the reaction force from the barbell. They're both acting downwards. And now the only force that's left to solve is the ground reaction force, this force down here. So we use the equilibrium equation to determine the reaction force from the floor. So that's the setup here. We've got the sum of all forces is equal to, we've got the force of gravity, the ground reaction force, and the force of the barbell, right? We have three forces in this scenario. So if we use this equation, we find that the reaction force from the floor acting on the athlete is 1,766 newtons, acting in the upwards direction, which counteracts the forces of gravity and the force exerted by the barbell on the athlete's hand. So if we take these three forces here and we line them up in their directions, we know this is the force from the barbell, this is the force of gravity, which means that the ground reaction force needs to be equal and opposite these two forces in order for static equilibrium to exist. Okay, let's do one last and slightly more complicated example. So Brian is a 200 kilogram strongman competitor who is competing in the truck pull event. And Brian wears a harness attached to a cable, and that cable is attached to a truck and a trailer. And Brian is also using his hands to pull on a rope that's attached to an immovable object in front of him. And he's attempting to pull the truck, but neither the truck nor Brian have started moving yet, which means that we have static equilibrium in this situation. So Brian pulls forward and slightly upwards on the cable with a force of 2,200 newtons acting at an angle of 14 degrees above horizontal. Brian also pulls on the rope with a horizontal force of 650 newtons. And we want to know how much force the ground is exerting on Brian's feet. So we're looking for this resultant force down here. Let's start with our free body diagram. That's always a good place to start. Remember that a free body diagram shows the external forces that are acting on a system. So in this case, Brian is our system, so we want to identify all of the external forces that are acting on Brian. We know Brian's mass, 200 kilograms, so we can find the force of gravity by just plugging in the 200 kilograms times the acceleration due to gravity. We have a force of gravity of negative 1,962 newtons. Okay. Next, we have the force that the cable exerts from the truck against Brian. So we know that the force Brian exerts on the cable is 2,200 newtons, but what is the force that's exerted by the cable on Brian? Well, remember that forces come in pairs, and the forces are equal in size and opposite in direction. So the force that the cable exerts against Brian is 2,200 newtons, but it pulls backwards and slightly downwards at an angle of 14 degrees below horizontal. Now we have the force that the rope exerts against Brian. We know that Brian pulls back on the rope with a force of 650 newtons, so the force from the rope must be 650 newtons as well, but in the opposite direction. So the force of the rope pulls forward on Brian in the horizontal direction. And there's one force left. We've got the ground reaction force, which should be pushing upwards and forwards on Brian. It's easier to represent this force with its horizontal and its vertical components. So remember from the first lecture video, that's the force of friction and the normal contact force, which is also called the ground reaction force, or GRF for short. Okay, so we have our free body diagram. Now we need to actually complete our static analysis by calculating the force that the ground exerts against Brian. A trick to simplify a more complicated problem like this one is to use two equilibrium equations. One that represents the horizontal component of that net external forces, and then one that represents the vertical component of the net external forces. If there's no horizontal acceleration, then the sum of all horizontal forces must be zero, and the same is true for the vertical forces. So the equilibrium equation, the sum of forces is equal to zero, it just becomes two equilibrium equations, one for horizontal forces and one for vertical forces. And in order to use these equations separately, we need to make sure that all of the forces in our free body diagram have been resolved into their horizontal and vertical components. And most of the forces in this situation already are, except for the force of 2,200 newtons from the cable, this force here, because that force is acting at an angle of 14 degrees below horizontal. So the first thing we need to do is resolve this force into its vertical and horizontal components. So these two components here. Okay, so if we just use trigonometry, we find that the horizontal component is 2,135 newtons and the vertical component is 532 newtons. So if we redraw the free body diagram with that force resolved into its components now, it would look like this. So we have the force of gravity acting down on Brian, which is 1,962 newtons. Then we have the force of the rope pulling forward on Brian, which is 650 newtons forwards. And next we have the force from the cable pulling backwards on Brian. And this force is now broken down into its components. So we have a horizontal component of negative 2,135 newtons and a vertical component of negative 532 newtons. So now we're ready for the static equilibrium equations. So if we start with horizontal static equilibrium, we have the force of friction, right? This force down here, the horizontal component of the force from the cable, and the force from the rope. And if you just simply plug all of those into your static equilibrium equation, knowing that the sum is equal to 0, then you can isolate for the force of friction. So by doing that, you end up with a force of friction of 1,485 newtons or 1,485 newtons in the forward direction. So next you solve for the vertical ground reaction force. So using the same static equilibrium equation, but this time you're doing it for the vertical forces. So vertically we have the ground reaction force, the force of gravity, and the vertical component of that cable force. We end up with a ground reaction force, so vertical component of 2,494 newtons positive, so acting upwards. And that makes sense, right? Given our free body diagram, the ground reaction force should be acting upwards on Brian. So there's just one last thing. We should determine the resultant of the ground reaction force and the force of friction, but we also need the direction of this resultant. So to do this, we use the Pythagorean theorem to find the magnitude, and then we use trigonometry to find the direction. So using the Pythagorean theorem, we find that the resultant force is 2,903 newtons. And then in this case, we can use the vertical and the horizontal components to find the angle of the resultant force, which is 59 degrees. So let's finally write our super important therefore statement. It should look something like this. So the resultant force exerted by the ground on Brian is a force of 2,903 newtons acting forward and upward on Brian at an angle of 59 degrees above horizontal. And that's this force here that we just resolved. So let's just summarize the steps involved in determining reaction forces in a static situation. So first, you isolate the system in question from the environment and you draw your free body diagram. Next, you show all the external forces that act on the system. And don't forget the force of gravity. Then you have to resolve any forces that aren't perfectly vertical or horizontal into their respective vertical and horizontal components. And if you have vertical and horizontal components, then you use the Pythagorean theorem to calculate the vector sum or the net force of the resultant horizontal and vertical forces. And then finally, you use trigonometry to determine the direction of this force, which is basically the angle that it makes with horizontal. Okay, we learned so much this week. In this lecture video, we really put together the two first videos and learned about free body diagrams and how they're useful for solving problems in static equilibrium, which we basically call a static analysis. Now, I know this was a lot of information, and as I'm sure you've figured out by now, biomechanics is all about practice. So I've made sure to include many sources for you to check your understanding of the content this week. Don't feel like you need to go through it all very quickly this week, but just know that it's there to help you to make sure that you learned all the content this week. And of course, I'm always here to help you as well. So just reach out if you have any questions or any concerns.